visited UK, London or South part, but this is my first time to visit this northern part of UK, and I really enjoy it. And today I'm going to talk about the work done in last year with Mendel Guen and Mitsuko. And Mendel Guen was a PhD student of Mitsuko Unzo at the North Carolina State University. But from this autumn, he moved to Durham University as a postdoc. So he will join this UK scientific community. So, okay. And today, so my talk is about Wilson-Hooft classification, about gapped classification scheme for gapped phases for the SU and gauge theory. And if I have a time, I'm also going to talk about n equal 1 star, but I'm not sure if I have a sufficient time. But yeah, let me first focus on this Wilson-Hooft classification. And what's that? And so this is the classification scheme for the gapped phases. And so first I want to tell you a motivation. So motivation is so since for the gauge theory has several kind of mechanism creating mass gap, such as the confinement and confinement. And so we want to have some kind of systematic classification scheme how that kind of mass gap is created in 4D gauge theories. And in order to discuss confinement, so Wilson considers that people notice that local order parameter given by original developed by Random is not so powerful enough to classify gapped phases of 4D gauge theories. And Wilson considered that instead of using local order parameter, loop operator plays an important role. And this is now called as Wilson loop, and it is formally given by this kind of path-ordered product of gauge field. And the meaning of this Wilson loop is basically a word line of test electric charge. So let's assume that this loop C takes a form of, say, this is a imaginary time, and this is one of the coordinate of space. And assume C takes this kind of rectangular form with length T and length L in the horizontal direction. And if we compute this Wilson loop, expectation value of Wilson loop, then by cutting your space-time by this kind of constant time slice, then there is a one positive electric charge, E plus E. And here there is since this is crossing this constant time direction in the opposite way, so this is a negative charge electric particle. And if we compute this Wilson loop, then by computing this expectation value, it turns out to this kind of exponential form times T times B of E bar L. And this B of L is basically telling the interparticle potential. For this test electric charge. Yeah. And then you can classify how confinement happens. So if B of E bar L is proportional to, let's say, some constant times, so if it is proportional to the length of interparticle distance, then this means that however particles are separated, another particle is attracted with a constant force to the other particle, and this means that test particle always has a inside a charge singlet tightly bound hadron, and this means confinement. And another possibility is if B of E bar goes to, as L goes to infinity, if it goes to constant, then this means the confinement. And basically, if system is gapped, so if for gapped system, Yeah, it is widely believed that so this is the unique possibility for for behavior of interparticle potential, and in this way, loop operator plays an important role to classify whether a system is in a confinement system or a deconfined system. And this is the basic idea of using loop operator to distinguish confinement and deconfinement. But later, so the Hooft noticed that so not only electric particle, so gauge theory also has a magnetic particle. And there is a counterpart of this Ward's line of this test magnetic particles. And he considers what is now recently called Hooft operator. And not only using Wilson loop, but also using this Hooft loop, we can get a final classification of gapped phases. And for example, as a matter of fact, if we consider, for example, SU2 Yang mills plus some adjoint particle system, there are three kind of gapped phases. Say one of them is Higgs, and there are two kinds of confinement state, confinement 1 and confinement 2. And oh, and yeah. And if we look at the behavior of Wilson loop, Hooft loop, and Wilson times Hooft loop, so each of them represent word line of electric particle, magnetic particle, and dionic particle. And in the Higgs phase, so Wilson loop obeys perimeter law. And let's see. And these Hooft or dionic operator obey the area law. While in confinement state, this Wilson loop obeys area law, area. And yeah, I do not explain what the difference of these two confinement states, but anyway, if the system is confined, Wilson loop obeys the area law. But on magnetic particle, so when we are in a confinement state 1, so this is in a perimeter law. And this dionic one obeys area law, and it's opposite for confinements, second confinement state. And what I want to emphasize here is if you just using Wilson loop, you cannot distinguish these two types of confinement states. While if you use and by using all set of line operators, then you can give a complete distinction between Higgs and two different kinds of confinement states. So using all kind of possible test electric magnetic particle plays a very important role to classify gapped phases. So yeah.
Is the possible the gauge group is SU2 or SO3? Are you going to talk about that?
Yeah, so in my talk, I'm going to focus on SU2, but also for SO3, same happens. Yeah.
And it's 3 plus 1 dimensions.
It's 3 plus 1 dimension. Yeah, I have to say 3 plus 1 D. Right.
Sorry, but each of these loops only exist in one specific global variant of the field.
So yeah, let me clarify what do I mean here. Yeah, but as a genuine line operator, yeah, what you said is completely correct. But here I'm also allowing using line operator, which is a boundary of topological surface. And yeah, I want to emphasize that using all set of lines are important. Yeah.
But I think that non-genuine lines cannot be used as order parameters.
Yeah, so let me clarify what, yeah, that is a point of my talk here. So I'm going to clarify that point. Yeah. Right.
Are there other phases than gapped phases?
That's a good question. Yeah. As far as I know, this is the unique three possibilities, but yeah, I do not know the proof. So yeah.
Okay.
Yeah. Do my best.
Coulomb phase.
Yeah, right. So, but assuming mass gap, do we have other phases?
Other gaps.
Yeah.
So you have the gapped phases.
Oh, yeah, right. So I'm focusing on gapped phases. Yeah.
Okay, maybe other phases, but not gapped.
Yeah, so there are several Coulomb gapless states, but yeah, for gapped states, I do not know. Yeah, so yeah, to my best knowledge, these are the only possibility for gapped states. Yeah. Okay, so this is why using all kind of loops are very important. But as pointed out, there's a mystery of using why we have to use all set of operators. And let me explain why this is mysterious. And so original derivation of this kind of classification by Hooft goes something like this. So he considers some kind of operator formalism, and he observes that if we look at the Wilson loop and Hooft loop as an operator in some constant space, in constant time slice, and assume that C and C prime are inside that constant time slice. And with that operator formalism, then if we consider commutation relation of Wilson and Hooft operator, we can show that this obeys this kind of commutation relation. So if you try to commute Wilson and Hooft loop, then there is a appearance of Zn phase for SUM gauge theory, depending on whether C and C prime are linked with each other. And from here, so Hooft, the guess, original guess, is so inside 3 dimension, these two lines can link with each other. But actually, this is just a constant time slice in 4 dimension. And if you go to path integral space-time picture, so everything should be understood within 4-dimensional picture, space-time picture. But inside that 4-dimensional, using that 4-dimensional picture, these two lines does not have a well-defined notion of linking number. So from this from this mysterious commutation relation, to guess that so at least one of W or H should form confining string. Then this world sheet of confining string is a surface in 4 dimension, and then so this mysterious commutation relation can be understood as one of confining string and the other charge. So this is how Hooft get the idea of Hooft derived the idea of Wilson-Hooft classification from this commutation relation. But from the modern viewpoint, this is mysterious, or this is incorrect. So in modern view, this is incorrect, and actual understanding is so at least one of W or H is not a genuine line. And this commutation relation is understood that, yeah. So yeah, so if we try to understand this one, then for SUM case, let's say this is Wilson loop in some direction, and let's say this is a Hooft loop H and this W. And in SUM case, so this Hooft loop is a boundary of some surface. So this is a surface. And that then one form symmetry generator. Then in order to, and let's regard this is a time direction, and in order to reproduce this commutation relation, so we want to consider the situation that this H leaves future compared with Wilson loop. But in order to keep this topological commute, since this surface is cannot just go through Wilson loop without paying any cost, so in order to completely exchange a location of Wilson and Hooft loop, yeah. So this surface should go across this Wilson loop, and when going across this gives an extra phase described in this leaking number. So this is a current or modern way to correctly understand this commutation relation. And so from this viewpoint, so in SUN gauge theory, Wilson loop is a genuine line operator, while Hooft loop is not a genuine line, but a boundary of topological surface. Yeah.
Sorry, the Wilson loop goes where? It's into the board?
Wilson loop is just here. Yeah, we want to express this operator formalism expression from the path integral viewpoint. And for this one, so compared with the time leaving the Hooft loop, so this Wilson loop lives a bit future compared with the Hooft loop.
Drew, it has 2 points. So where is the loop?
Yeah, so I couldn't write down the it's extended into fourth dimension. Yeah.
I think what this means is that this Wilson loop is charged under the 1.5.
Yeah, exactly.
Thing.
And the Hooft loop is living on the boundary of open surface for when that one form symmetry generator has a boundary. Yeah. So this is how we understand this commutation relation since Haroni, Seiberg, Tachikawa's seminar 2013 paper appeared. But then this brings us a question whether what is this original classification for gapped phases of SUN gauge theory? So one way to just understand it is this original derivation is just wrong. And this correct understanding of Wilson-Hooft commutation relation is just a classification of overall structure of gauge group like SUN or SUN mod ZN with this shift of discrete theta parameter, something like that. But Mendel asked me still this asked me in last year that since this Wilson-Hooft classification seems to be reasonable as a dynamical consequence, so is it really wrong or is it actually correct, and whether do we have some way to save this idea of Wilson-Hooft classification from modern viewpoint of one form symmetry? That is a question we'd like to answer, and our answer is this Wilson-Hooft classification also correct, while we need more discussion for its derivation. So and the idea is our system is we are considering QFT with Zn one form symmetry like for the SUN gauge theory with a joint particle. And let's assume that this is gapped. And try to write down the RG fixed point. And and our strategy is first to write down RG fixed point partition function. And doing some manipulation, we are trying to derive that Wilson-Hooft classification. So this is the idea we would like to take up. And as an answer for having this RG fixed partition function, so we assume that this Zn1 form symmetry is spontaneously broken. To some subgroup, let's say that small n one form symmetry, and stacked, and we also consider stacking of level K SPT state, asymmetry protection topological state of this unbroken symmetry, let's say the n. And in order to study this kind of system, so it's always convenient to introduce consider a partition function with background gauge field. So this B is a background. Zn gauge field. And in order to represent this scenario for SSB plus SPT stacking, we consider this kind of RG fixed form. Times e to the I.
So
Yeah, sure.
for the epsilon plus one adjoint fermion has many vacua, right? And you are focusing on one of them because there's a zero form discrete symmetry which is spontaneously broken.
Yeah, so depending on this matter contents, there can be more rich structure of zero form symmetry, but here we just focus on the one form symmetry and assume that the other symmetries are sufficiently broke. Or yeah, we are considering random.
You are turning on mass, not mass.
Yeah, right. Yeah, sure.
It's meaning of this SPT or just like compared to some other vacua?
Yeah, so actually, so that was my plan of second part of the talk, but yeah, actually all of these possibilities can be realized by n equal 1 the super means. Yeah, so depending on the vacuum configuration of scalar chiral multiplet, we can realize this SSB pattern, and by tuning the theta angle of this super means, we can also realize the level K SPT stacking. So yeah, this is all the possibility can be actually yeah, concretely realized in this n equal 1 star model. Yeah.
Actually, I'm confused with something that you're about notation. So the H is the Hooft line, which
It is the first line, yes.
but like I thought that what measures the charge of the Wilson line was like the integral of dual F or F, which was like a surface, not a line. And then there is like the Hooft line, which is a line, and what measures its charge in the integral of F. But in any case, like the two lines, they do not intersect. They do not link in particular.
Yeah.
I'm kind of confused with.
So in that sense, this Hooft line is not genuinely a line operator. So it is a boundary of the surface, but this surface can be topologically moved without changing the expectation value. That is the actual meaning of the Hooft loop in SUN gauge theory.
I thought what measures the charge of the Wilson line was the integral of like.
What measures this electric charge of Wilson loop is this surface operator. Yeah. So this yellow part of the surface, this surface part measures the electric charge. So this is a kind of integration of star F. Yeah.
What is link of C and C prime? Because in 4D they do not link, right?
All right. So what is actually linking is between Wilson loop and this surface.
Okay.
Yeah.
But I guess in the previous formula that you wrote, when there was linking on C and C prime, you had in mind that they are both on the space-like slice, and this is counting the intersections.
This is both on space like slice. Yes. So linking of space like between C and C prime. Yeah, yeah. And that actually, yeah, at least in simple situation, this actually match with linking number between this C and this surface. Yeah, yeah.
Yellow surface is not linking the Wilson, it's wrapping.
It's wrapping it. Yeah.
In the representation of it.
As though that was supposed to clarify.
Still true.
Yeah. And yeah, and and this is the RG fixed point partition function of this scenario, and this part represents SSB of Zn down to Z small n, and this part is a SP, a starting point SP system. And yeah. So yeah, correctly, yeah, correctly, we should have, yeah, in that cochain notation, we should have, let's see, Hooft pi over n. Yeah, this is contrarian. Divided by. I think this is more correct notation in cochain expression, and basically saying that because of this delta functional constraint, this capital B was originally modulo capital N integer, but because of this constraint, so B is now taking into N over small n times integer, and by dividing that factor, this B divided by this factor represents the background gauge field of this that small n one form symmetry, and it's positively again with the SP starting. Yeah, that is more correct way to express it. Yeah, yeah.
That's just a shorthand.
Yeah, this is just a shorthand continuum notation. Yeah. And so claim is for this RG fixed point, yeah, lines with perimeter are generated by W to the power of small n. See, and also let's see, for Hooft loop with power of small times W. Yeah, so claim is for this RG fixed point partition function. If we look whether Wilson loop and Hooft loop of a perimeter or area row, then the set of line operator of a perimeter row should be given by these, should be generated by these two line operator. And this is exactly what Wilson to Hooft classification says. So this part is Wilson to Hooft classification. So yeah, before proving the details, so I want to give one message. So yeah, by just looking at the Wilson loop, actually we can see how spontaneous symmetry breaking occurs from electric one form symmetry to the smaller subgroup. But the one way to detect this level K of SPT stacking, we should use non-genuine line operator. So this part is non-genuine line. And using this electric charge and reading off the electric charge of this non-genuine perimeter line operator, we can identify what level K of SPT is stuck to this SSB, naive SSB scenario. So in this way, so using the non-genuine line plays an important role to get a recover original Wilson to Hooft classification of gapped failure for the gaps. And let me go the proof. So basically, we are going to show that for this partition function, we would try to read off which line operator obeys perimeter law. And the idea is, so we compactify 4D to 3D by considering M4 as a choice of four-dimensional space-time manifold to be M3 times S1 with fixed length. And the size, and we said that so size of M3 is much larger than size of or length of S1. And I assume that this is much larger than one of mass gap. And first, so this part of assumption, so this large inequality between mass gap and other direction for manifold is important so that so fixed point formula is applicable to evaluate partition function in this system. And another energy scale separation here is important so that our effective theory becomes three-dimensional. So first, we consider this kind of introduce this kind of scale separation, and
Are you assuming anything on the topology of M3? Are you assuming anything on the topology of M3?
so here, so that M3 can be arbitrary. Yeah, topology of M3 can be arbitrary.
S3 is okay.
S3 is, yeah, maybe S2 times S1 or T3 or something.
Interesting, yeah.
All right. And so in this scale separation, so originally we start from a system with 4D one form symmetry. But now, because of this scale separation, our effective theory becomes three-dimensional. And this 4D one form symmetry produces this 3D one form symmetry and zero form one form zero form symmetry. And basically, so this first one form symmetry is acting on a loop operator that is living inside this large M3 direction. And this zero form symmetry acts on a loop operator that wraps along this S1 direction. So which looks like a point-like operator for this 3D. And in this setup, so we perform gauging Z and 0 3D. And then then this part is gone by gauging, but we obtain the dual symmetry. In 3D. And from this dual symmetry, so this part is a dual of this electric zero form symmetry, and this acts on Hooft loop, and original one, this part acts on Wilson loop, living in three dimensions.
Can you explain again why you are one over mass gap is much smaller than the size?
Basically because we are going to evaluate the partition function after this gauging, and in order to evaluate it, so we would like to just substitute this setting into this fixed point formula, and basically by introducing this large scale separation between mass gap and whole size of four-dimensional manifold, that allows us to use this fixed point formula. So that is the idea. So if they are comparable, there could be higher excited state contribution to this partition function, and it may give a phase transition, and this use of this RG fixed point formula is not may not be justified. But here, by introducing this scale separation, we are excluding that subtle possibility.
I guess that my conclusion is that with this assumption, your theory becomes effectively three-dimensional only below the scale of confinement.
Right. Yeah, by introducing this scale separation between M3 and S1. Yeah.
No, but the last one.
Last one. Yeah, yeah.
So when the mass gap, if the mass gap is much smaller than your energy scale, then this is not going to be true. Then it
Yeah. So we are assuming the mass gap is sufficiently large compared with the
right, yes.
infrared scale introduced by
scale of confinement, you cannot reduce the theory from 4D to 3D. It's just below the scale of confinement.
Yeah, right. So what's your question again? Yeah.
That you want to classify phases.
Mm-hmm.
So you using this 3D theory. So I would expect that this 3D theory is already important at the scale in which you see the separation of phases, which is the scale of confinement.
No, yeah. So basically, we are just saying that. So when we put theory on this M3 times S1, and if this M3 is much larger than S1, then its KK mode along this S1 is negligible.
Okay.
Yeah, and we reach the 3D effective theory, but still this S1 is still much larger than compared with the mass gap. So for the phase is already fixed by this length scale, and what we are discussing is much larger compared with that dynamical scale. So for the formula is still applicable. So that's a point.
Clarify the formula you wrote for the one form symmetries on the bottom here. Do you still have a linking between them?
So sorry, which formula are you?
Bottom here you have ZN. You have these two ZN one form symmetries. Do they link in three-dimensional space like you had?
They can link.
I mean, do they commute? Is there a commutation relation like a pickup?
No. I don't think in this setup So since we cannot no longer use force direction, so that linking doesn't occur.
But now they link, right? In 3D they link.
In 3D they link, and it seems that they wouldn't commute, but that they would commute by contribution.
But that requires time, right, to discuss the commutation relation. So since this is now already classical, just a kind of statistical field, so yeah, we do not discuss that kind of operator commutation relation.
Understand. You can still talk about one form symmetries, whether there's a two group implicit in what you're saying, and you can ask whether there's a extension term. Probably not using the right words, right physical words.
Let's see. So yeah, let me tell several things. So yeah.
In physical terms, I'm asking, can you fix each of these one form symmetries individually? Like,
yeah, we can fix one form symmetry individually. Yeah.
Maybe another way to ask this question is whether there is an anomaly for 2U1 or 2ZN1.
Answer is no. And yeah, let me tell some formula which would answer your questions. Yeah. So let's compute the back so one this 3D partition function. So yeah, so original for D one is given by. And from this, we would like to derive 3D partition function for, let's say, so for this one, let's make for be the magnetic for the background field. Let's see. This is B electric. And we would like to compute B. And in order to do it, so we basically show the so what we are going to perform in this manipulation is compute this 3D partition function using this formula. And basically this says that so original this B it splits into that 3D one form symmetry part and zero form symmetry part. So we separate this original 4D two form gauge field into 3D one plus AA which theta over L. And this is a background field for zero form electric one form symmetry and zero form electric symmetry and one form electric symmetry in 3D perspective. And we promote this background gauge field for zero form electric symmetry to a dynamical field. Your object is B tilde M. And important property is so important property is so we can show that from using reflection positivity. This 3D with partition function with generic one form symmetry background is positive definite. And so because of this positive definiteness, yeah, so your question of whether mixed anomaly between these two exists or not, the answer is no. So there is no mixed anomaly between. Yeah. Yeah, so let's see. In order to prove this reflection positivity, so we just basically use yeah. If we sum this kind of thing, we can up to suitable normalization. So it's just okay to. So since this A is just a cyclic or ZM gauge field, so just copy and summing up them up is still okay and gives the same formula. And so by applying this equality into this one, and we can actually show that so let's see. Yeah. Well. Yeah, so background field for B is, yeah. So this is say M3 and this background gauge field for one form symmetry is a codimension to topological objects. So let's say this is B. Yeah. And let me take this is a reflection plane. For one form symmetry. And And using this kind of formula, so counterpart of this one is a codimension to a codimension one object. So this corresponds to DA one. And the insertion of this one. And so by copying it and using its topologicalness, so we can just copy the same object here. And we can relate these two by reflection, and we can, and you can also take this yellow codimension to object also in a reflection invariant way. Then you can say that this is a reflection invariant setup. So for unitary theory using reflection positivity, that partition function has to be semi-positive definite. Yeah. And so that's the idea. Yeah.
Doesn't that show that the norm is semi-infinite? We just say that there could be sort of no constraint.
No, yeah, not on. So sorry.
I thought if you're using this argument, it looks like you're showing that the absolute value is positive definite. If you're looking,
No, I don't think so. In reflection, reflection invariant setup for unitary theory partition function itself should be semi-positive definite. Yeah.
Okay, maybe I don't understand your.
Yeah.
But the claim is for some specific topology or which what partition function is this? Is that torus?
Let's see. Okay. Yes, this M3 should also have some reflection plane. Yeah. And assuming that M3 is invariant under that involution, and then we can show this claim. Yeah. So right. So manifold M3 manifold itself should have non-trivial G2 involution. Yeah. Yeah. And
Are you assuming that you don't have fermions in 4 dimensions?
it may have fermions. Yeah.
I was thinking that if you have fermions in 4 dimensions, when you compactify on the circle, you can have massive fermions in 3D. So when you integrate them out, you can induce a Chern-Simons level for the gauge field in 3D.
In general, yeah, answer is yes. Yeah.
This is a question. It's likely not to be true.
So of course, for example, if that fermion has chiral symmetry, and if you also introduce background gauge field for chiral symmetry, answer is yes. But here we only introduce background gauge field for one form symmetry. Yeah, right. So if theory has more symmetry and they may have if they have mixed anomaly with one form symmetry and introducing their backgrounds, stories are completely different. But here we only introduce a background gauge field for one form symmetry.
If there is a Chern-Simons level, then there is a pure anomaly for the electric symmetry.
Yeah.
Even only for BA without putting BM.
Yeah. If that situation occurs, answer should be yes. But I don't think from this argument for unitary theory, I don't think it happens. Yeah. Yeah. Right. Okay. Then so since we now have sufficient technique, so let's just compute this one for this fixed point partition function. So and let's see. So since we are having this delta function should apply to each component, and we get okay. Yeah, and this part is for the integral, but computing this part should give nk over 2 pi. Yeah, right. So we can combine them as yeah, so sorry, something is, yeah, this should be capital. And yeah. Yeah, right. Yeah, so just doing a simple computation of the Fourier transform, we reach the formula that we get delta and VE times delta n over n. Yeah. And looking at this formula, so first term, so this part tells that so Wilson loop to the power n obeys perimeter law. And the second part tells that, let's see, h to the n divided by n times w to the k obeys perimeter. So in other words, so by going to 3D and doing a dual transformation just for zero form symmetry, we are having the setup that have both electric and magnetic one form symmetry. And in this specific setup, we can just discuss SSB of electromagnetic one form symmetry. And we now show that so this one does. And one spontaneously broken to some order group H generated by and 0 and points. So
Just one question about the formula. So there's this integral in dA,
yeah,
delta NA.
yeah.
So NA is 0. And the exponent NA is 0. So
So this A is, yeah, I have to say this is capital N gauge field. So basically this says that so integration of A along some one cycle should be n over n times integer. But since original n can be modulo capital N, so still we are having small n. Yeah. So still we are having non-trivial integral and non-trivial summation, and we find that this part should be 0 modulo capital N. Yeah. I mean, yeah.
I did not understand why the delta functions tell you which Wilson and Hooft operators have a parameter law.
Okay, yeah, I see.
Then you explain it and explain it to me later.
Yeah. But yeah, maybe since time is up, so let me finish. So what we have shown is so originally so Hooft derived Wilson Hooft classification with his genuine insight, while that original logic does not make sense in modern viewpoint. But now using the logic of one form symmetry and using the clear distinction between genuine and non-genuine line operator, that so actually original claim on the Wilson Hooft classification for gapped phases of 4D gauge theory can be recovered by using this kind of logic. So by doing compactification and gauging of the zero form symmetry part of electric symmetry gives this kind of so recovers this classification proposed by Wilson and Hooft. So in some sense, so this kind of non-genuine line also plays an important role to distinguish several gapped pages of confinement set. So that's everything. Thank you very much for.
Thanks, very nice talk. Any questions? A few minutes for questions.
I have a question. So in general, in the continuum, there's always this statement that SPTs are relative among each other because you can always add a counter term.
Yeah, right.
And modify the SPT. So in your original description in 4D, so you have like Higgs confinement 1 and confinement 2. I think there is no like intrinsic way to say which is confinement 1.
That's true. So you
distinguish the two.
Yeah, so UV regularization scheme here is assumed to be fixed, and under that fixing of UV renormalization, we are talking about the relative SPT compared with that.
My question is, how do you understand this ambiguity from your 3D construction?
So definition of that Hooft loop has some subtlety under that UV regularization, and so here we fixed that regularization scheme of the Hooft line, so that it is consistent with that SPT stacking. Yeah.
So you're saying that if you change regularization scheme, you're gonna change what you call Wilson and Hooft in 3D.
Yeah, especially the Hooft loop is very subtle, and that basically because that Hooft loop is not a genuine line operator. So yeah. So because of that subtlety, so these arguments should be understood under fixed UV regularization.
Well, you said that you could get this partial spontaneous breaking of the one form symmetry from an n equals 1 star.
N equals 1 star, yeah.
How do you get the subgroup without changing the global form of the gauge group?
Let's see. Yeah. So let's see. So n equals 1 star, starts from n equals 4 super-M, so it has 3 complex argument scalar. Yeah. And the superpotential is given by trace x1, x3. So this is the n equals 4 part, and we can also add. And in order to go to n equals 1 star, we add this extra term to the superpotential. And solving this equation of motion for x, you get the fuzzy sphere configuration. And depending on the solution of that fuzzy sphere configuration, so you can get the Higgs of SU. Yeah, you can get this kind of Higgsing, and depending on that vacuum configuration, this small n level changes. And basically, you can get all possible Higgsing pattern.
Oh, okay. You're looking at like specific chambers.
Yeah. So right. So, taking specific fuzzy sphere solution, yeah, you get that Higgsing pattern. Yeah.
So on the complexification, what is the boundary condition that you take for the fermions? Like
for fermions here, we didn't specify, but natural one would be let's see, anti-periodic, I guess. Yeah.
So it's a thermal circle.
Let's see. Yeah, as far as I understand, as long as assuming that the system is gapped, it doesn't matter. But as far as I know, assuming that system is gapped, it is okay to take any boundary condition for fermion parity part, I think. Yeah.
You took the scale of confinement is much like the confinement kicks in before the complexification.
Yeah, right. That's the assumption of the scale separation. So that part should help a lot. Yeah.
Thank you. So thank you. This